Earlier in the course, we represented the projective plane as the surface you get if you identify the edges of a rectangle like this. Each opposite pair is glued together with a twist. You may also know something else which we call the projective plane, namely the plane in which we do projective geometry. In this program, we'll explain why that geometer's projective plane is topologically equivalent to the surface described by this gluing procedure, the topologist's projective plane.
Let's start with a reminder of how the geometer defines the projective plane. The geometer's model consists of the ordinary plane, R2, with some extraordinary points thrown in, the ideal points. And there's one ideal point for each direction in R2, each set of parallel lines in R2. In other words, all these parallel lines are regarded as meeting at infinity in an ideal point. You can think of this point as being on the horizon. Actually, you have to think of the opposite horizon point, behind you, as being the same point as this one. That is, the two opposite ends of a set of parallel lines are regarded as the same. They determine the same ideal point. Well, you may also know a more symmetrical description of the geometer's model in which there are no special ideal points. All points look the same. In this version of the projective plane, a point is represented by a line through the origin in R3. You have to imagine each of these lines as being extended infinitely in both directions. And in fact, to avoid confusion, we use the word ray rather than line through the origin. Now, don't think of this ray as made up of a lot of points. Think of it as a single object representing a single projective point. And then the projective plane consists of all possible rays. Well, that may seem a strange way to represent projective points, but it corresponds precisely to the geometer's plane model. We take a standard embedding of R2 in R3, parallel to the xy plane, but not through the origin. Then each ray corresponds to the projective point where it meets R2. And the rays which don't meet R2, the ones in the xy plane which are parallel to it, well, they correspond to the ideal points at infinity. And notice there's one ray in the xy plane for each direction in R2. So we do have an exact correspondence. Now, there's an advantage in this symmetrical version of the geometer's model. Unlike the plane, we don't have to imagine two opposite horizon points as being a single ideal point. Here, each ideal point is a single object, a ray, just like all the other points. Well, that's dealt with the geometer's description of the projective plane. How does it connect with the topologist's model? It's difficult to see the connection because this version has rays, which don't look like the points of the topologist's model, and the geometer's plane model has imaginary points at infinity. What we need, instead of a plane R2, is something curved which will intersect all the rays, so we don't have to invent imaginary ideal points.
So instead of a plane, let's try using a sphere. Now, we're all right as far as intersections are concerned. All the rays intersect the sphere, including those corresponding to ideal points, the horizontal rays. But another problem has emerged. Every ray meets the sphere in 2 points, not 1. Therefore, each point of the projective plane corresponds to 2 points on the sphere. So to get a genuine model for the projective plane, we're going to have to identify antipodally opposite points. This is the notation for that. This means consider the points of the sphere S2, but think of each pair of antipodal points as a single projective point. So in this new model of the projective plane, we're back to having to use our imagination again to identify pairs of points. But this time we have a symmetrical model because we identify every pair of points. Well, in order to move closer to the topologist projective plane, we're going to eliminate some of the redundancy by taking just half the sphere. Let's take the bottom half. Each ray still meets the hemisphere, so we still get all the points of the projective plane as points of intersection with the hemisphere. And now the only rays which meet the hemisphere twice are on the equator. So if we identify these pairs of points, we've got another new model of the projective plane. The points of the hemisphere with antipodal pairs on the boundary identified. And of course, these special points correspond precisely with the ideal points of the geometer's model. Well, in fact, we've now arrived at the topologist projective plane. To see that, you just have to flatten this hemisphere into a disk. Here's the flattened hemisphere, and those antipodal points have become opposite points on the boundary. So the projective plane consists of all the interior points plus the identified pairs on the boundary. And now all you have to do to see that this is the same as the topologist projective plane is to deform the disk into a square. And the gluing of the edges here is really the same as identifying diametrically opposite points on the boundary.
So, the geometer's projective plane is equivalent to the topologist's projective plane. Let's just summarize how we got here. The geometer's plane model consists of R2 together with the ideal points, one for each direction. An alternative way of describing this is to represent each point as a ray through the origin of R3. The horizontal rays correspond to the ideal points of the plane model.
This description led to our first new model, the sphere with antipodal pairs of points identified. Then removing half the points to get the bottom hemisphere, the only points which remain as identified pairs are those on the equator, which in fact correspond to the geometer's ideal points. Then flattening the hemisphere gives a disk with opposite points on its boundary identified, which is equivalent to the topologist's model.
So, we can take either the square or the disk as our topologist's model. And what we've done effectively is to contract R2 onto the interior of the disk and bring the ideal points in from infinity onto the boundary of the disk. Well, later on, we'll come back to the geometer's plane and look at some geometric figures and see how they look to the topologist. But first, Colin's going to use some of the new models he's constructed to study some topological features of the projective plane.
First thing I want to show you is that the projective plane is non-orientable. Remember, a surface is non-orientable if it contains a Möbius band. Well, we can find a Möbius band quite easily in the spherical model. These two circles subdivide the sphere into three regions, two disks around the north and south poles, and between them a cylinder with the equator as its center line. In fact, the cylindrical region is a Möbius band in the projective plane. Why is that? Well, opposite points are identified, so we only need to look at half the cylinder. For example, this point is also represented at the back, so we don't need the front half. Now, each projective point on here is represented by a single point, except on these edges, where we still have to identify pairs of points. And notice that involves gluing in opposite directions to achieve the correct identification. In other words, I have to give this a half twist before gluing. And here's our Möbius band. So the projective plane is non-orientable. we're now in a position to tackle an interesting topological question. We've seen that part of the projective plane is a Möbius band. What about the remainder? What is it topologically? Well, these two pieces are both disks, but they're identified point for point. So they represent a single disk in the projective plane, for example, the bottom one. Therefore, the projective plane consists of a Möbius band stuck onto a disk. In fact, they're stuck along their boundaries because the boundary of the disk, this bottom circle, is in fact the boundary of the Möbius band. To see that, start here on the boundary of the Möbius band and go along the red part. That's this half circle, and then follow it by the white part, which is this half circle. But look, if I replace the front half of the cylinder, then that white half circle is the same as this bottom half circle here. So the second half of the boundary just completes the bottom circle. And of course, you could have chosen the top circle instead to represent the boundary of the Möbius band, because the two circles are identified. But again, the top circle is just the boundary of the top representation of the disk. So in fact, we've now got another description of the projective plane. It's a Möbius band and a disk stuck together along the boundaries. Well, with all these identified pairs here, it's very difficult to see how these two pieces fit into the topologist model. So let's get rid of as much redundancy as possible. Let's remove the top disk, and as before, let's remove the front half of the cylinder. And here's what we get. Here's the Möbius band, and you've seen that these two edges have to be identified with a half twist. And here's the disk, and half its boundary is already glued here. And the other half has to be glued to the other half of the Möbius band's boundary. So we get these identifications. And now if we flatten this, you can see how the disk and Möbius band fit into the topologist model. Just deform the flat picture into a square, and you get the topologist model. So all you need to do is to draw this curve on the topologist model, and you can see it directly as the union of a Möbius band and a disk glued along their boundaries. Well, now let's look at some ideas from projective geometry and interpret them topologically. First, the idea of a line on the projective plane. It turns out that each projective line is the center line of a Möbius band.
Well, to see that, just consider any line on the geometer's plane. It corresponds to a plane of rays. And you can see that rather more clearly over here, where I've also included the spherical model for later. Now, here's the line of points on the geometer's plane, and this is the plane which corresponds to it. Now you can see on the spherical model that the projective line is represented by a great circle. And this band, either side of the great circle, is in fact a Möbius band. Well, why is that? It's fairly easy to see if you first consider a horizontal plane, because that would give the equator as the projective line. And you've already seen that a band neighbouring the equator is a Möbius band. Well, the whole thing's completely symmetrical, so the angle of the plane doesn't make any difference. And that means that a band neighbouring one great circle is topologically the same as a band neighbouring any other great circle. And so this is just as good a Möbius band as the equatorial one.
Let's see this Möbius band without all the identifications by looking at the hemisphere model. Now you can see the Möbius band very clearly because the top edges are identified in opposite directions. Here's what it looks like on the flat representation. The band looks rather like this, and the identification of opposite points gives these identifications for the Möbius band. So any projective line is the center line of a Möbius band. Well, actually, we could call it the center circle because these two endpoints are identified. So the line is a simple loop. In fact, it's a topological circle. Here it is again as the center circle of an intact Möbius band. And we call such a circle orientation reversing because having a Möbius band neighborhood implies that orientation is reversed when you travel round the circle.
So there's one geometric idea interpreted topologically. A line on the projective plane is an orientation reversing circle. You can actually see that the line is a circle even on the geometer's plane model because the ideal point at infinity in this direction is the same as the ideal point in the opposite direction. And when you glue together the two ends, you get a loop. But the fact that that loop is orientation reversing, well, that's not quite so easy to see on the geometer's model. We'll come back to that at the end of the program. First, we've got a different problem, because if a projective line is topologically a circle, then how does it differ from an ordinary finite circle? Is there any topological difference?
Well, here's a familiar example of a finite circle on the projective plane, an ellipse. That is the intersection with the plane of a cone of rays. And on the hemisphere model, we actually get a small circle. And such a circle is not orientation reversing in the projective plane. That's easy to see if we flatten the hemisphere. We still have a topological circle, and it's clear that a small neighborhood of it is just an annulus or cylinder, not a Möbius band. So there is a real difference between a finite circle and a projective line. As objects in themselves, they're both topological circles. But as circles embedded in the projective plane, the small circle preserves orientation, whereas the projective line reverses it. To end the program, we'll take the topological ideas we've seen and interpret them on the geometer's plane. Let's see if we can actually distinguish on the plane the two pieces which we know the projective plane consists of, the disk and the Möbius band, which are glued along their boundaries.
Just imagine that this plane goes off to infinity and includes the ideal points at infinity. So this represents the geometer's projective plane with a disk cut out of it. So what remains should be a Möbius band, and the boundary of the Möbius band should be this red and white circle, the disk's boundary. In fact, I can go further. Here's a projective line. On our other models, we've seen that this is a topological circle running round the center of a Möbius band, like this. So we should be able to recognize everything outside this disk as a Möbius band, with this line as its center line and this circle as its boundary. Well, it certainly doesn't look like that at the moment. It'll help us if we first draw some line segments on the Möbius band. What we do is choose a point on the boundary and draw a line which meets the center circle. Then we go round the boundary, repeatedly drawing line segments, until eventually we meet the center circle where we first met it, but this time from the opposite side. I could cover the rest of the band with line segments if I carried on round the red half of the boundary. I then start hitting all the points on the center line which we've hit before, but this time from the opposite side. And of course, what's going on here is that you're forced to come back on the opposite side because of the half twist in the Möbius band. Let's see if I can reproduce that behavior with line segments on the geometer's plane with the disk removed. Remember, this boundary circle is what we think of as the boundary of the Möbius band. And this projective line, we hope, is the center line of the Möbius band. So to copy this picture, I need to draw line segments from the boundary circle to the projective line. So I take a point on the circle, and I draw my first line segment to meet the projective line. Then another line segment, and so on. But where does this line segment meet the projective line? It looks as if it's aiming away from the projective line. Well, if I draw the next line, you'll see what's happening. It goes out to the ideal point and comes back from the opposite side, because remember, an ideal point is a pair of identified points opposite each other. And so on. Until when I'm halfway around the boundary circle, I meet the projective line again where I first met it, but this time from the opposite side. And as before, if I carried on, I'd go out here and come back to meet the projective line once again from the opposite side, and so on. So we get exactly the same behavior as we had for the Möbius band. And you've seen what that behavior means. It means we've got a half twist. Somewhere out at infinity, there must be a half twist which brings you back on the opposite side of the projective line. So the geometer's plane minus a disk is a Möbius band, with this circle as its boundary and this projective line as its center line.